Okay, so today's topic is molecular simulation methods in computational chemistry. And by simulation methods, I mean generally a computer model of what's going on, typically in a bigger, complex molecular system, or maybe there's many molecules, something like that. Individual molecules, maybe we can do particular specific calculations on those to get their properties, and maybe that doesn't rise to the level of a molecular simulation. But the simulations typically are of a couple types. Either we watch how the system moves around in time, that's going to be called a molecular dynamics simulation. The dynamics implies we're watching things in time. Or we'll do calculations of a different type to help us get the properties of some complex system by sampling many different possible configurations it could be in. And those will be Monte Carlo simulations. And either one could be called a molecular simulation. I'm going to more or less follow along some material in chapter 6 of Andrew Leach's molecular modeling book, and I can recommend that one for this kind of material. Okay, so first off, let's introduce a few concepts. And one of those is phase space. So if anybody has taken some classes in classical mechanics or maybe statistical mechanics, you may know all about phase space. But if you haven't heard of this before, by phase space, we're really talking about the sort of hypothetical mathematical space that could be spanned by a set of coordinates. And the coordinates we're talking about is the 3D Cartesian coordinates of all the atoms. That I'm going to lump all those together in a collective variable bold R. So that'll be the Cartesian coordinates of atom 1 and atom 2 and atom 3 and all the atoms, and we'll make just a big vector of these and call that symbol R. And then we also need to know the momenta, typically, of those atoms, and those we will collect into a variable P. Okay? So if I have n atoms, then each one could have an x, y, and z coordinate. So there are 3 n coordinates for the locations of the atoms, capital or bold R. And then each atom can have a momentum in the x or y or z direction. So there are 3 n momenta coordinates p, and the total number of coordinates is then 3n for r and 3n for p, which gives you a total of 6n coordinates. And the space of all possible sets of those 6n coordinates, which we might denote as parenthesis p comma r, is called phase space. So it's a 6n dimensional space, so it's kind of a high dimensional space. Okay, so let's talk about Hamilton's equations, which are the more generalized form of the equations of motion. So if I know P at time t and R at time t, so all the momenta and all the positions at a given t, then I can figure out what they ought to be at some future time, as long as the future time isn't too far in the future, and as long as I know P and R accurately, I can use Hamilton's equations to calculate what they will be at a future time. And this is kind of the generalized version of Newton's law, and we formulate it in terms of what's called a Hamiltonian operator. So if you've taken a class in advanced classical mechanics, you know all about this. If you haven't, maybe this is news to you. But the Hamiltonian operator is just a mathematical object that basically captures the kinetic and potential energy that all the particles feel. Okay? In fact, it's the same idea as the Hamiltonian in quantum mechanics, except in this talk we're talking about the classical version of that, which gives you Hamilton's equations. So the Hamilton's equations I show on this slide, the rate of change of the positions of the particles, and I could denote some particular position with a subscript I. The rate of change of that with respect to time is just the partial derivative of the Hamiltonian with respect to momentum for that same particular coordinate I. And then similarly, the rate of change of the momentum is very similarly the partial derivative of h with respect to r. This one happens to have a minus sign in front of it. But they have a nice kind of mathematical symmetry to them. So it's a differential equation, but it's not an infinitely complicated one. And using that, you can tell what P and R will be in the future. And then if you map out what P and R are at your initial time, you might call it T0, and then a future time T1, and another future time T2, then you trace out what's called a trajectory through this phase space. And that tells you just how all the coordinates change and how all the momenta change during the course of time. Obviously, if I start with a different set of initial conditions, maybe the molecules start in a slightly different set of Cartesian coordinates, then that will propagate to a different trajectory. Okay, and that's the idea of Hamilton's equations. Now, if that's a little too fancy for you, that's okay. A lot of times when the molecular dynamics programs are written, people go ahead and formulate them in terms of the simpler and maybe more familiar Newton's equations, which is just essentially F equals ma. So that's fine too. The force, can also be written as the derivative of the potential V with respect to r coordinates, and then m is the mass, and then acceleration is also the second derivative of the position with respect to time. And in MD simulations, what you do is you solve this equation kind of numerically, and that allows you to go from coordinates r at some given time to future coordinates at some future time. There are various techniques to do the numerical integration, and I'm not really going to go over those in this intro talk, but you should be aware that it is a part of the problem you have to solve if you're going to write a molecular dynamics code. And there are things like Verlet integrator and leapfrog integrator, and they have slightly different techniques to solve this differential equation and to propagate their trajectory. Okay? All right, so let me introduce the basic molecular dynamics procedure. First off, I start from some initial set of coordinates and momenta for all the particles in the system. And this is non-trivial because maybe you don't know a reasonable guess for where all the atoms are. You might hope that the software you're using maybe can give you a reasonable guess if you give it, what the molecules are and whether it's a liquid or a solid and kind of at what density maybe. You could hope that it could give you a reasonable guess. But the more complicated the system, the more components it has, the less trivial it is to come up with a chemically reasonable, a physically reasonable guess. So this is a little non-trivial even for the very first step. But once you have that, and you must have it before you can start an MD simulation, then you compute the energies and forces on all the atoms. How would you do that? Well, in principle, with any method that gives you energies and forces. It could be quantum mechanics, it could be molecular mechanics. Typically, though, in the context of this talk, we're talking about molecular mechanics or force field methods because we're looking at bigger systems and we want to be able to simulate those for a non-trivial amount of time. Then, once you have those initial conditions and then initial energies and forces on all the atoms, you integrate Hamilton's equations or Newton's equations by taking you do this numerically. You take some short time step, maybe it's 1 femtosecond, which is 10 to the minus 15 seconds. Maybe it's a half a femtosecond. But you take a time step and then you propagate those equations, and then that gives you the momenta and the positions at a future time. Not very far in the future, but nevertheless in the future. And that time step needs to be short because typically we're assuming that the forces are constant during that time step, and that will be true for very short time steps. Then that gives you a new set of coordinates and a new set of momenta, and then you take another step. And you repeat this. You take another step, another step, another step. You keep using Newton's equation or Hamilton's equations to get the future P and R, and you do this again and again and again. You would like to run the simulation as long as possible because a lot of chemical phenomena, don't happen on the order of a femtosecond. And so you need to run the simulation for many time steps if you want to see what's happening on, say, a nanosecond time scale or a microsecond time scale. You're going to have to run many, many, many time steps if you're going to try to achieve something like that. So MD will be a little easier for chemical phenomena that happen very rapidly. Not all chemical phenomena happen rapidly. Some of them are very, very slow, and then that can be quite a challenge. And how long you run it really depends on the system you're looking at, what property you're interested in, and how much computer time you have, and how patient you are. So it's a compromise between all of these things. Now, unless you are somehow injecting random forces into the simulation, and there can be reasons to do that, otherwise the trajectory is going to be deterministic from the initial configuration. So if I were to start from exactly the same initial set of Cartesian coordinates and momenta, then in principle, if I ran the simulation 1,000 times, I should get the same trajectory 1,000 times. Okay? And so Newton's equations are basically deterministic equations as long as you start from the same set of coordinates. However, I just mentioned at the very top of the slide that you don't always know necessarily where the atoms are starting from. You're just sort of making something up that's reasonable. And so if I were to start from a different set of initial coordinates, I would trace out a different trajectory. So if there is some uncertainty in what the initial coordinates are, which there almost always is, then I may want to run many trajectories starting from many different initial conditions to hopefully get a representative and reasonable picture of what's happening. Okay. From a molecular dynamics simulation, MD simulation, I can extract the time average of any property. So if A is some property, and we'll talk about some properties in a minute, then I can compute, well, what's the property of the system for a given set of momenta and positions at time t, and then if I just integrate that over all times that are in the simulation up to a final time tau, then in the limit as tau goes to infinity, that gives me the macroscopic average property of the system. Okay? So this would work great on paper, but of course I normally can't afford to run the simulation forever, and so the simulation I have to put in a practical limit for the time here in computing the property, and maybe I can't run the simulation long enough to get a really good average that would match experiment. So that's one of the challenges. Typically, this integration, you don't do it analytically because I don't have an analytic formula for this. What I've done is I have a set of P's and R's, and if I know how to go from P and R to get the property of the system A, then I have this at various time steps, and then I just compute this for each time step and average over all the time steps. And M might be the number of time steps, it might be 1,000,000, it depends on the simulation. But I would do the average this way. Okay? Now, in reality, this is all very hard. Okay, so I showed a couple equations and maybe it sounded okay, I hope. But there are some issues. One of them is that, if I got a beaker of some particular solvent, then I might have a mole or 10 moles of solvent in the beaker, and then a mole is a very large number of particles, okay? 6.022 times 10 to the 23rd particles. And that number of particles is too large even for a giant supercomputer. There's just too many of those things. So we can't simulate a mole of particles. It's just not going to work. So we have to have various ways to cheat, and let me tell you about some of those in this talk. Yeah, and even if you could somehow do the simulation, which you can't, you can't even store all the Cartesian coordinates and momenta for that number of particles. This is simply too many. Okay, so it's essentially impossible to do this really for a mole of particles. We will have various ways to cheat that I'll talk about, and that's also a reason why, even if I cheat, I need to use classical mechanics, because I need each time step of the simulation to be as fast as possible. And one of the biggest ways to simplify this complexity and to cheat on the computational cost is to use periodic boundary conditions. If I had a lattice, a crystal lattice, then that's a regular solid structure that's the same if there's only one molecular atom in the crystal. It's the same in the x and y and z direction, and it goes on that way for essentially infinity, not really infinity, but for a long, long distance. And there I can take advantage of the mathematical periodicity of the system and impose what are called periodic boundary conditions when I do the simulation. If it's not a crystal but a liquid, then it's not perfectly the same in every direction, but to an approximation, I can imagine that small details aside, it basically looks the same in the x, y, and z direction. And again, there are ways for me to use periodic boundary conditions. Okay, so what's a periodic boundary condition? Well, imagine I have a more or less homogeneous system, like a liquid or a solid, and I just simulate a chunk of it. So in this diagram on the right, I've got a bunch of different atoms in green and different atoms in pink. And you can see it's a kind of a repeating pattern, so it looks like maybe a crystal in this case, made out of two different things, maybe sodium and chloride or something like that. And I can kind of mark out a little box of this, and I see that if I repeat this box in the x, y, or z direction, well, it's only two-dimensional in this diagram, then it looks the same. If I were to move that box up or down or to the left or the right, it's a repeating pattern. So that's your sort of central unit cell, and you do the simulation using that, and then you kind of account for the idea that there are sort of regular mathematically repeating patterns of that going off in each direction. Okay? And so, for example, if I had this green atom and in my simulation it moved outside the box, then knowing that it's periodic, that's the same as having it move back inside the box from below. So I can account for things moving inside or outside of the box and still use this repeating pattern. And obviously, if I'm doing the simulation of what's in the box, even if I have some tricks for accounting for regular images outside the box, that's a much simpler proposition than trying to literally simulate the entire thing, which is really impossible. I can use some tricks like distance cutoffs if I want to restrict the interactions to maybe just what's inside the central box and maybe the nearest boxes. Maybe I say if you're, 2 or 3 or more boxes away, you're too far away to really matter. And that's the simplest way to cut down on the number of interactions. There are slightly trickier ways, like Ewald summation techniques, to take account of repeating images that go off to infinity. But that's the basic ideas. I look at what's in my box and maybe the nearest boxes, and that is, a practical thing that you could actually do. The central box, I've drawn it as a box in this little diagram. It could be a cube. It doesn't have to be a regular cube. It could be, if it's a different kind of solid, it could have different dimensions in x, y, and z. That's possible. Other things are more complicated, are possible as well. You could have truncated octahedrons. You could have more complicated shapes that sometimes do come up in chemistry. Now, let me say a little more about choosing the initial conditions, okay? I've hinted that this is maybe not a trivial thing to do, especially because we can't run the simulation forever. So the fact that I have a finite amount of time that I can run the simulation, unless I have the world's biggest computer and a lot of patience, that means I need to start off with what's already kind of a reasonable situation. And then hopefully I'm in the ballpark of real physics, and then the simulation is more meaningful when I start it up. Okay, so what do you want in the initial conditions? Well, I've mentioned you want it to be chemically and physically reasonable. What does that really mean? Well, if you have a liquid or a solid, it should have about the right density. I mentioned that. You also want to avoid sets of Cartesian coordinates where I have a high energy configuration. Why? Because Boltzmann tells us that the high energy configurations are just less probable. And so I probably don't want those in my initial coordinates because they're just not very likely. I would like to start with a representative set of coordinates, and those will typically be ones that are lower energy, more stable sets of configurations. So that's what we're looking for. Now, if I'm lucky enough to start off with a simulation where I'm trying to simulate a crystal lattice, then if I know something about the crystal structure of that molecule, then I'm off to a great start because I can just start with the idealized crystal lattice. If it's a liquid, it may not be in a perfect lattice, but I can still maybe start off with some kind of crystallographic lattice as a guess geometry, and that could still get me sort of reasonable distances between atoms and different reasonable densities. I can pick initial orientations if I have non-spherical molecules kind of randomly. So maybe I know about how far apart the molecules are and I can get that right, but I don't always know, which way this one is twisted compared to this one. And there I can just guess randomly and randomize each one, and hopefully that gives me something reasonable. Maybe I have some experimental data I can try to sort of match that up with, and maybe I don't. It depends on the situation. If I'm lucky enough to have an X-ray structure of it, then great, I can start with that. I may have that, I may not, it depends. For sure, I want to check once I've generated this, or once the program I'm using has generated this initial set of configurations, I want to check to make sure I don't have atoms colliding with each other. That would definitely be bad, a low probability, high energy situation. And maybe to help avoid that, I can run a small geometry optimization first to let the molecules try to move down towards some equilibrium situation. So that would be one technique. A very common technique, even if you do all the stuff above, is what's called equilibration. Okay? So frequently, even if you're trying to be very careful with your initial set of coordinates, it's just very hard to guarantee that they're reasonable. So what you often do is what you could call kind of like a pre-simulation, or technically it's known as an equilibration step, where you run your molecular dynamics simulation for a while. How long depends on the system and the technique, but you run it for a while, and then that's called the equilibration step, and you're just hoping that the MD simulation pushes apart any close contacts and kind of lets things settle down a little bit and gets rid of any bad things that are in your initial configuration. And once you've equilibrated, then you typically throw away all that data and you say, oh, I was only doing that just to iron out the problems in the initial configuration. And then you consider the MD simulation to start for real, and you start to take that data to actually use and analyze. You can monitor the simulation to try to see when the equilibration has happened, okay? For example, if I start with a liquid simulation and I just put all the molecules apart at an exact lattice separation for the closest reasonable crystal structure or something, Then there are techniques to monitor the simulation to watch when have I moved from what's essentially a solid guess configuration into something that really looks more like a liquid. And there you can watch for the melting of it. And then when you see that it's melted and it's really a liquid, then you say, okay, now I've equilibrated. And there are various techniques to try to do this. I can also just make sure that the various thermodynamic properties of the system have leveled off. So I can monitor things like energy, volume, temperature, and make sure they're not bouncing like crazy, but that they start to level off and have a kind of a stable, small fluctuations. And that's a good sign that I've reached equilibration. All right. Now, if you know a little stat mech, you might have heard of something called the ergodic hypothesis. That basically says that if the time average of some property A, whatever property it is equivalent to its so-called ensemble average. So I showed this equation before where I said here's the time average. If I know P and R and I can compute a property from those, then I do this at all these different times from the initial time to the end of the simulation, and the limit of long simulations, that gives me the macroscopic property averaged. Sometimes this is not a convenient way to do it. So an alternative approach then is to say, well, instead of a time average, I'm going to average over all the P's and R's, the momenta and positions, in the simulation or in phase space. And if I know how to go from a given P and R to calculate property A, I assume that here as well. But here, there's no time. Here I multiply each of the integrands A of P and R by the probability that I get that P and R. Okay? So this is really now is an average over P's and R's, but some P's and R's are less probable than others. And so I have to multiply by the probability that I'm at that particular point in phase space, P and R. And if I do that in principle, I get the same average. So the Boltzmann distribution tells me that only low energy configurations are probable. That exponential was minus E over kBt. And if I have a high energy, then I have e to the minus some big number, and that decays very rapidly. So it's a very low probability. Hence, it may be possible to do the simulations more efficiently if I can spend more computer time sampling the low energy configurations. If the computer spends a lot of its time thinking about these high energy things, they're not very probable, and their contribution is going to be very minimal. And so if I could bias the simulation away from those low probability configurations that don't contribute much, then that would be a more effective use of my computer resources. And it's also true for this exactly the same reasons that the low energy configurations make the dominant contribution to the partition function Q. So what Monte Carlo does is it is a biased simulation approach that tries to sample these low energy configurations directly, and I'm using that second equation I had where I just average over P's and R's, and I don't need time even. So that's the essence of Monte Carlo. I try to find the low energy configurations that are more probable, give me a bigger row, and I sample those, and then for those I calculate A for that given P and R and the probability that I'm at that P and R, and I average that way with that double integral over P and R. So typically, in fact, the way Monte Carlo works in practice is that we normally just sample different R's, and we typically don't necessarily even need the momenta or the time variable t at all. Okay, so let's talk about the Monte Carlo procedure, because it's not very complicated. I can teach you this in one slide and you'll know how it works. You start from some initial configuration, just like you do in molecular dynamics, okay? From the previous configuration, or in the first step, from the initial configuration, I generate a new configuration by moving some one or more atoms in a particular direction by some random amount, okay? So I sort of randomly perturb my configuration by moving some atoms around. Then I calculate, if I did that, and that's just done at random, what would the potential energy of the system be if I move the atoms that way? And I'll call that V nu of R. And the potential energy typically only depends on R and not P, and so that's why the P sometimes is less important in Monte Carlo, because I can get the potential energy without it. If the new potential energy is less than the old one, then we'll call that a good step in Monte Carlo. And then that will become my new configuration for the next step. If it's not, then I do a little random step. So what I do is I generate a random number on the interval from 0 to 1, and then I compare that to the Boltzmann factor, the energy weighted factor, for the energy difference, e to the minus v nu minus v old over kBt, okay? And so that Boltzmann weighting tells you for this energy difference, how likely is it that I could jump that high up in energy to achieve this. And if the random number is higher than that Boltzmann factor, then I reject the move and I just keep the original configuration, okay? Otherwise, the move is accepted and then that new configuration becomes the next step, next state. And then I do this over and over and over and over, many, many, many times, until I run out of patience or I convince myself that the simulation is converged. And then the property is just computed by averaging over all the Monte Carlo steps. And so you do need to record what all your P's and R's were so you could compute the property of each of those. Or in this case, maybe you only need R if the property only depends on R. And then I just do that average, okay? Let me then see if I can summarize the difference between Monte Carlo and molecular dynamics. So MD needs the forces on all the atoms because it needs Newton's equations, okay? So it needs a force, F equals ma. But Monte Carlo typically just needs the potential energy because it's only about potential energies and whether they're big changes or small changes. Molecular dynamics thus is concerned with P and T, whereas Monte Carlo isn't. It just needs R's. Molecular dynamics typically keeps N, V, and E constant, or maybe N, V, and T constant in some MD simulations. And those are called either microcanonical or canonical. Monte Carlo typically is focused on NV and T, which is a canonical ensemble. So MD could be either of these, really, but MC is typically more on NV and T. And it is possible to modify molecular dynamics and Monte Carlo to sample from other ensembles, as well.